Hello, this is Richard Hammack's Calculus 1 course. We are in part 4 of the course on applications of differentiation. Today, in lecture 37, we'll talk about a technique called Newton's method. This is an application of derivatives to the algebraic problem of solving equations. Simply put, it's a method for solving equations. It goes all the way back to Isaac Newton, who was one of the inventors of calculus. This method hinges on the idea of linear approximation, which we introduced in the previous lecture, and I'll remind you of how linear approximation works. If you have a function y equals f of x, you can take an x value of, say, x equals a, plug that into the function, you get a point a f of a on the graph, and there's a tangent line there, shown in red, and that straight line is the graph of a linear function called L of x. And as we discussed last time, L of x equals f of a plus f prime of a times the expression x minus a. That's definitely a linear function because the x here is to a power of 1 and everything else is a constant. When you distribute into the parentheses and collect like terms, you can get it into the form of y equals mx plus b. But we're going to leave it in this form for convenience. We will be especially concerned with where this red line crosses the x-axis with its x-intercept right here. That x-intercept is the number a minus f of a over f prime of a. Perhaps the easiest way to see that is to plug this number into x in L of x and confirm that you really do get a y value of 0, so you're on the x-axis. Plugging this in for x, it would also be plugged in here. So imagine plugging a minus f of a over f prime of a in right there. The first thing you do is you subtract an a, which would make that a disappear, and you're left with this term in parentheses being equal to minus f of a over f prime of a. It's being multiplied by an f prime of a, so the f prime of a is canceled, and you just get this whole term right here being negative f of a that's added to that f of a, and that's 0 right there. So we'll use this simple scheme in Newton's method. And here's the way it works. Newton's method is a way of solving the equation f of x equals 0, for solving an equation that has the form of f of x equals 0. And I'll show you a picture of this. Think about the graph of y equals f of x. And imagine you're looking for the solution to the equation f of x equals 0. That would be right there. At that x value, f of x equals 0. So that's the solution. And we want to find it. Newton's method works like this. The first thing you do is you make an educated guess at what that solution might be. And you'll probably be wrong. But your guess, let's call it a sub 1. That's your guess at the solution. So your first step in Newton's method is to guess a solution a sub 1. As I said, it's unlikely to be the actual solution to the equation. But what Newton's method is going to do is to convert that guess into a better approximation of the solution, and then continue the process so you get better and better and better approximations to the solutions. You'll create a sequence that converges to the solution, and you're going to use linear approximation to do that. The first thing you do is you take f of a1, and you think of the linear approximation at a1. It's a tangent line right here, and it crosses the x-axis at a point, let's call it a sub 2. Now, what is a sub 2? It's where the tangent line crosses the x-axis. So it's given by a sub 2 minus f of a sub 2 over f prime of a sub 2. So there we go. A sub 2 is this expression. Now a sub 2 is still not a solution, but notice that it's closer to the solution than a sub 1 was. So what we're going to do is iterate this process. We're going to look at this better solution, a better guess at the solution, a sub 2, and take the linear approximation to f of x at a sub 2. And we get a tangent line here that crosses the x-axis at this point, which we're going to call a sub 3. Now, what is a sub 3? It's where this tangent line crosses the x-axis. That's given by this expression with the a sub 2 plugged in for the a. So this a sub 3 right here would be equal to a sub 2 minus f of a sub 2 divided by f prime of a sub 2. And bear in mind that you computed a sub 2 in the previous line. So you see here that a sub 3 is a better approximation to the solution than a sub 2 was, but it's still not the solution. So what do? You take the linear approximation to f of x at a sub 3. You go up to f of a sub 3, establish a tangent line, look at its x-intercept. That's given by this equation with a sub 3 plugged in for a. So this number, we'll call it a sub 4, and it would be got in the following way. We take the a sub 3 that we obtained here and plug it into the expression to give the x-intercept of this tangent line. That's a sub 4, which is a sub 3 minus f of a sub 3 over f prime of a sub 3. And you're even closer to the solution, but you're not quite there. So you just continue this process. And what happens is that you very quickly get numbers a4, a5, a6 that are getting closer and closer to the actual solution. As you can see in this picture, for large n, the number a sub n is a very good approximation to the solution. And for practical purposes, you can get that a sub n to be as close to the solution, the actual solution of f of x equals 0, as you want. So that's Newton's method. We'll phrase it this way. Newton's method is a method to solve the equation f of x equals 0. And from the previous page, the first step is to guess a solution, a sub 1. Then you let a sub 2 be a sub 1 minus f of a sub 1 over f prime of a sub 1, as we did in the previous page. And once you've got that a sub 2, you create a sub 3 as a sub 2 minus f of a sub 2 over f prime of a sub 2. And that's a better approximation to the solution. And you keep iterating this process. If you arrive at an a sub n, you can get the next approximation to the solution, a sub n plus 1. It's going to be equal to a sub n minus f of a sub n over f prime of a sub n. And you can take this process as far as you want to go. These numbers, a1, a2, a3, a4, a5, a6, and so on, get to be a better and better approximation to the solution, the actual solution of y equals f of x. You might write it this way. The solution to f of x equals 0 equals the limit as n goes to infinity of a sub n. That's Newton's method. Let's look at an example. Let's solve the equation x cubed minus x plus 1 equals 0. So we're looking for a value of x that makes this equation true. And notice that this equation has the form of f of x equals 0, where f of x is x cubed minus x plus 1. So we want to find the solution to this equation. Notice this is a cube. It's not a square, so you can't use the quadratic formula here. And in fact, if you play around with this to solve by factoring or so on, you're going to run into some obstacles. Nonetheless, we want to find a solution to this equation. Now, off to the side, here's a rough sketch of our function f of x equals x cubed minus x plus 1. It's got this basic shape of a cubic graph. If you plug in -1 to f, you get a positive value. In fact, you get a positive value. F of -1 would be positive 1. And if you plug in -2 here, you'll get a negative value. So by the intermediate value theorem, there's got to be some point right here where the graph of f of x crosses the x-axis, and that's your solution right there. That's what you want to find. So let's apply Newton's method to this. The first step would be to guess a solution to this equation. And it looks like the actual solution is somewhere between -1 and -2. So let's make our guess as a sub 1 equals -1.5 right there. And you can see that's probably not quite right, but it's pretty close. So that's our initial guess. Now the way Newton's method works, remember, is that anytime you have a sub n, you can find the next a sub n minus n plus 1 by the expression an minus f of an over f prime of an. So there it is right there. And let's actually work out what this is. An minus this fraction, and on the numerator it's f of a sub n, and f of x is x cubed minus x plus 1. So f of a sub n would be an cubed minus an plus 1. Now what about the denominator? It's f prime of a sub n. Here's our f of x. F prime would be 3x squared minus 1. So f prime of a sub n would be 3a sub n squared minus 1. So we've just worked out here that whenever we have an a sub n, we can get an a sub n plus 1, which is a better approximation to the solution, by this equation right here. And we'll organize our work with a table showing the a sub n values. Initially, all we have is a sub 1 equals minus 1.5. That's our guess. So we'll tally that right here. Next, we need to find a sub 2, which will be a better approximation to the solution. And to get a sub 2, we would take our a sub 1 and plug it in here to get a sub 1 plus 1, which would be a sub 2. So right here in the a sub n, here, 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 and there, we'd plug in minus 1.5. And if you do that, I won't go through the gory details of it, but if you do it, you might need a calculator, might be helpful. But you'll get a sub 2 equals negative 1.34782608. And I'm going to terminate this at the 8th decimal places. Those decimal places do continue after that. So that's a sub 2, negative 1.3, and you can see here that that's going to be a little bit closer to the solution than was negative 1.5. But we don't stop there. We're now going to compute an a sub 3. So this a sub 2, which is this number, would plug in for the a sub n here, 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 and there, and would give you a sub 2 plus 1, which is a sub 3. So doing that, plugging this a sub 2 into this expression will give you a sub 3, which is this value. And again, I'm truncating the after 8 decimal places. It does continue after that. We're just rounding off here. we'll get the solution to 8 decimal places. So about negative 1.325. So the next thing you'd want to do is compute the next approximation to the solution, a sub 4. So you take this value of a sub 3 and plug it in here. With a sub 3 plugged in, this expression would give you a sub 3 plus 1, which is a sub 4, and it works out to be negative 1.32471817, approximately. Again, the decimal places keep going, but we're terminating after the 8th decimal place. Then you take this a sub 4, you plug it into this expression to give a sub 5, and if you check it, you'll get this. And iterate again, take this number for a sub 5, plug it in here, and you get a sub 5 plus 1, or a sub 6, and it turns out to be this. Now notice that a sub 6 is exactly the same as the a sub 5 value that we have here, and there actually is a difference, but that difference occurs after the 8th decimal place. For all intents and purposes, this number a sub 6 is the solution to f of x equals 0, or x cubed minus x plus 1 equals 0, to 8 decimal places. So rather than continuing, let's say that 8 decimal places is good enough for us, and that's our solution. X is approximately equal to a sub 6, which is to 8 decimal places, negative 1.32471795. And you can check that, plug it in here to f of x, or rather plug it in right here, and the value you'll get will be something like 0.00000001, very, very, very close to 0. But good enough for 8 decimal places. And again, if you want more accuracy, go to A7, A8, and so on. You can get the solution to any desired degree of accuracy. So this is how Newton's method works. You guess at a solution, you use linear approximation iteratively to get better and better and better solutions. For our next example, let's solve the equation sine of x equals x squared. We want to find its solutions. Just looking at this, you can probably see right off the bat one solution that's easy to find. It's x equals 0. Sine of 0 equals 0, and 0 squared equals 0. So x equals 0 solves the equation. That's one obvious solution. We got that not by using Newton's method or any other technique, but just by looking at the equation. But you might wonder, are there other solutions? Think about the graph of x squared, shown here, and the graph of sine of x, shown here. You can see that these two graphs intersect at 2 points. There are 2 x values here, and also it looks like one here, where sine of x equals x squared. And the one that's right here, that's x equals 0, where the graphs cross. That was our obvious solution. What about this other solution that's right there? At some number, it looks like it's slightly less than 1. You get sine of x equals x squared. Let's see if we can find that solution. We can use Newton's method to find it. And before we get started, I want to point out that if you tried to solve this equation, to find this other solution, by algebraic techniques or trigonometric techniques, maybe take the sine inverse of both sides and so on, you'd run into trouble. It would be impossible to isolate the x. You couldn't get it as x equals something. You're always going to have an x on both sides. So familiar techniques of solving equations are going to fail us for solving this equation for the solution here. So let's apply Newton's method. The first thing we want to do in Newton's method is to make a guess at this solution. And how about we make a guess of A1 equals the number 1. That's pretty close to, it looks like that's pretty close to the actual solution. So that's our first step in Newton's method. A1 equals 1. In applying Newton's method, we have to apply it to an equation of the form f of x equals 0. That's the way Newton's method is set up. But notice we don't have that here. It's sine of x equals x squared, not f of x equals 0. To apply Newton's method, the first thing we would do is write this equation in the form to which Newton's method applies, f of x equals 0. And you can get that really easily by subtracting an x squared from both sides. So rather than solving sine of x equals x squared, let's solve an equivalent equation, sine of x minus x squared equals 0. So that's of the form f of x equals 0, where f of x is sine of x minus x squared. And we can apply Newton's method to that. Now remember, Newton's method works by taking a guess at the solution and getting a better approximation to the solution from that guess using linear approximation. And the way it works is once you have an a sub n, like this a sub 1, you can find a sub n plus 1, the next approximation, as a sub n minus f of a sub n over f prime of a sub n. And let's work out what this would be. Bring over the a sub n. F of a sub n would be this equation with a sub n plugged into it. That's sine of a sub n minus a sub n squared. And we divide by f prime of a sub n. And look at f prime. It's cosine of x minus 2x. So f prime of a sub n on the denominator would be cosine of a sub n minus 2 times a sub n. So this equation is saying whenever you have an a sub n, you can find the next approximation, the better approximation, a sub n plus 1, by plugging in a sub n to this expression. As we did in the previous problem, let's organize our work with the table for the a sub n values. We started off with our initial guess, a sub 1 equals 1. And as you can see, that's wrong, but only slightly so. The next step would be to plug in a sub 1 into this expression to get a sub 1 plus 1, or a sub 2, and plugging into 1 into the sine and the cosine and squaring it here and times 2 there and so on, and making sure your calculator is in radian mode. Plugging in 1 for all the a sub n's, you will get, if you try this, your a sub 2 is 0.89139959. And this is to 7 decimal places. Of course, these trail off after that, but let's just work with 7 decimal places and round off at the 8th decimal place. So that's a sub 2. And notice 8.9, that's a little less than 1, so you're a little closer to this unknown solution. You want to get even better, so you need to compute a sub 3. You take this number and you plug it in for the a sub n's in these 5 places, and you'll get a sub 2 plus 1, which is a sub 3, and plugging in this number here, you'll find that your a sub 3 is this number to 7 decimal places. It's a little bit smaller than what we got before, so you can see you're kind of marching closer to that question mark. Next, do a sub 4. Take this a sub 3, plug it in for the a sub n's, and you'll get a sub 3 plus 1, or a sub 4. You'll find that a sub 4 is this. And iterate again take this a sub 4, plug it in for the a sub n's here, and you'll get a sub 4 plus 1, or a sub 5. And I worked this out on my calculator, and I got this value. And notice that to 7 decimal places, that's exactly the same as a sub 4. Now, there was a change, but it happened after the 7th decimal place. So our point of view here is that 7 decimal places is good enough to get a very good approximation to the solution. So we actually picked up 2 solutions to this equation, sine x equals x. They are the obvious one, x equals 0, and also x is approximately equal to 0.8767262, which is right there. If you want more accuracy, just take it to A6, A7, A8, and so on. By letting a sub n get bigger and bigger and bigger, the n get bigger and bigger and bigger, you get a closer and closer approximation to the solution. But we got it to 7 decimal places right here, so we're going to stop there. So there we go. Our second example, we found all the solutions to sine x equals x squared. So this is Newton's method. You may want to practice a few of these on your own to get the hang of it. I should be quick to add that Newton's method is not something that you're going to use every day. In fact, you may never use it. And the reason is that there are a lot of software packages out there that solve equations. And they use techniques like Newton's method. And since it's programmed into the software, you don't have to carry out this procedure. But I think it's good to know how these things work and to know what's going on in the background. It's good for your mathematical understanding of what's going on in the software. So that's it. We'll just do 2 examples. I do want to point out some things that can go wrong that you might want to watch out for. First of all, you might be solving an equation like the one graphed here, and maybe at some iteration you get an a sub n that's like this, where the tangent line is equal to 0, or has slope 0, and that's not going to cross the x-axis at all. And in fact, if you think about the formula for a sub n plus 1, it's dividing by an f prime of a sub n, so you're going to divide by 0 there. And at that point, the program just crashes. So that's a pitfall. Another thing that could happen in Newton's method that would go wrong is you might have something like this f of x, and you're trying to find the solution. And actually, you can see the solution right there is x equals 0. And maybe you make a guess of a1 right there. And to find a2, you use linear approximation. You go up to the graph, you do the tangent line. It hits right there. That's a sub 2. And then you want to find a sub 3, so you take the linear approximation at a sub 2. And doing that, you go here, look at the tangent line, and it got right back to a sub 1. So that's actually what you get for a sub 3. You applied linear approximation at a sub 2. You're back here. So a sub 3 is equal to a sub 1. In the next iteration, you want to find a sub 4. You take linear approximation at a sub 3. You look at where it crosses. It crosses right there where a sub 2 was, and that's a sub 4. And at this point, you can see that your approximations, so-called approximations to the solution, are going like a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6. They're just bouncing back and forth, and they're never converging to the solution of 0. This is an infinite loop. Well, that's something that could go wrong too. So you can see here that Newton's method is a little bit of an art. You have to sort of know what you're doing when you're using it and be alert for these pitfalls. Another thing you'd have to watch out for is this. Suppose you had a function like this one, where f of x equals 0 has no solutions. This graph never crosses the x-axis. And imagine that you just blindly applied Newton's method to find a solution. You made a guess of a sub 1, you got to a sub 2, you did linear approximation again, a sub 3 is there, then a sub 4 is here, and then you find a sub 5, it's right there. Well, those numbers are just bouncing around randomly almost. They're never converging to a solution because there is no solution. So you might file this one into the maxim garbage in, garbage out. You applied the program to an equation that has no solution, and you should expect garbage. Another pitfall is this. Suppose you have an equation that does have solutions, and maybe you're looking for this solution right here. You want that solution, and you go, okay, well, I'll take a guess that's pretty close to that, like this a sub 1, and you're trying to get this solution, but look at what linear approximation does. It takes you down here. You cross the x-axis right there, and you can see that when you apply Newton's method with a sub 1 as your starting point, you're going to get this solution. You wanted this solution, but you're going to get this solution. So you might file this under uncritical use of Newton's method. It's an art. You have to use it in the right way and know what you're doing when you use it. In conclusion, we have Newton's method, a way to solve the equation f of x equals 0. You make an initial guess, a sub 1 at the solution, and then you get increasingly better and better approximations to the solution by the scheme outlined here and that we discussed today. The bigger and bigger n is, the better and better an approximation a sub n is to the actual solution of the equation. You could write it this way: the solution is the limit as n goes to infinity of a sub n. Although, as we saw today, for all practical purposes, you can usually take n equals to be 6 or 7, and you've got a really good approximation. I want to point out here, in conclusion, that there's a limit involved, and take note of that limit. It's a fact that the deeper you go into calculus, the more limits you're going to see. You might be under the impression that limits were used for the definition of a derivative, and then once we have those derivative rules, we're not going to use limits much anymore. But that's actually not the case. Calculus is filled with limits, and not just for the definition of the derivative. You're going to see more and more limits, so it's important to be able to evaluate them quickly and easily. In our next lecture, we're going to talk about what's called L'Hopital's rule. It's a method of evaluating limits using derivatives. It will be our final application of derivatives. We'll spread that over 2 lectures. It's an important topic. Much more important than Newton's method, I might add. So tune in for that, and I'll see you next time. Goodbye.